right? Name is Lon Stevens. The title is Attenuating Acoustic Effects and HDD Performance. I'm not going to go over, there's a lot of different things that we can do that can be done to attenuate the acoustic effects on drives. I'm just going to talk about one of the many things that we're kind of working on at Seagate. I'll just go down. So I'm a principal engineer at Seagate Technology. I spent first 12 years doing aerospace. When I worked at Pratt & Whitney, the cooling air was 1,000 degrees Fahrenheit, so we're going to try to keep everything below 1,000 degrees Fahrenheit here as well. It's all the same physics, right? So kind of a little bit of background. The hard disk drive, we're putting more and more data on these hard disk drives. I remember when I first met my wife, she had a computer and it had 500 megabytes. And it took all night, I think, to send it to the printer. I think it was like an 8-page report, and she started it the night before, and when I got there to pick her up, it was on the last page. It took the whole night to print. So it just keeps getting bigger and bigger. Right now, we're at about 500,000 tracks per inch. If you're not familiar with a drive, you have all these tracks going around on these disks, and what you do is the head's following that disk, and if you get 500,000 tracks in an inch, that's a lot. And so what I wanted to try to do is kind of give a perspective here, and that's what the charts are. The one on the left, on the bottom, if you take a sheet of paper and you turn it on its side and you look at it, you can put 2,000 tracks on that edge of the sheet of paper if it's a 500,000 tracks per inch. And then as in the next coming years, we're going to get going to 700 and 800,000 tracks per inch. It just shows how small this is. As you go up on the left, you've got the dust particle diameter. You can put about 1,000 tracks on a diameter of a dust particle. You can do the same thing for about a hair diameter. Bacteria, it's about 600 tracks. And then what I did, I kind of zoomed in because you can't see anything anymore. So if you go to a virus diameter, about 2 tracks per diameter. And then you can, wavelength of ultraviolet light, granted wavelengths, there's several wavelengths, but I just kind of took in the middle and you get about 5 tracks. So it kind of gives us that perspective of how small these tracks are and how difficult it is for the head to stay on these tracks. And it's making it harder for the servo system to be able to attenuate the effects of external vibration that are sent to these drives. And vibration can come from several different locations. You got operational vibrations. Maybe your system's running and someone pulls out an enclosure right above or right below. Maybe somebody's putting in a rack right next to it. Maybe someone's walking by. So you have these operational vibrations. You have drive-to-drive interactions. You can have a drive right next to it that's rotating, doing some seeks, and if the system's not designed well enough, that vibration can go around and get transferred to the drive next to it. And so that needs to be looked at as well. You could have nearby equipment. Maybe someone wasn't smart and they put a data center right next to a train track, and so a train comes by and you get a lot of vibrations that way. All these things can push the track off it, or push the head, the reading head on the drive off the track. And one of the things that we're seeing more and more of are the acoustic effects. These fans or air moving devices, as the fan speeds increases, the noise increase, and that acoustic noise can also affect the drive, the performance of the drives. Now the drives nowadays, they can filter out most of the frequencies below 2,000 kilohertz, but fans can generate noise up to the 20,000 kilohertz range, and so there's a lot of noise that can be transferred to the drives. On the left just shows kind of it's just a sample of one fan. The blue on the bottom is just background noise, and then the other plot is that frequency range, and so you can see you get a lot of broadband noise out to like 20 kilohertz, and you get a lot of spikes, these tones, blade pass frequencies usually. All of these things can affect the drive. And so one of the things we've done is we've been looking at how much of an effect this has on the drives. And the trend towards these higher AMD speeds is becoming more and more of a factor. On the left, it shows we used a microphone near a sample slot, and there's 3 plots there. The top 2 plots are for 2 different locations in the back row of an enclosure with the fans at maximum speed. And then the bottom line is for that one of those same slots, but the fan is at 70%. You can see that that acoustic plot has dropped quite a bit. It's 10 dBs or so, just by reducing the fan speeds. More importantly, the two plots on the right, these are included in the Hard Disk Drive Performance Degradation Susceptibility ASHRAE Technical Committee white paper from 2019. But you got three curved lines. These are all drives in the back end of an enclosure. You got a max, an average, and a min. The two horizontal lines are one's at 20% and one's at 10%. And the vertical axis is percent degradation. And then the horizontal axis is fan speed. So you can see for this drive and for this system, it's going to be different for all different enclosures and different drives that are put in there. You can get almost an 80% reduction in performance at the max fan speed with this enclosure. And if you drop that fan speed down to about 12,000 RPM, even the worst case drive has dropped below that 10%. So you can see how much that fan speed can affect the performance of the drive. The two plots, the one in the middle is for 1 megabyte sequential write, and the one on the right is for a 4K random write. But it shows how big of an effect AMDs can have on these drives. And why are the AMD fans increasing? There's a number of reasons. Three of them I'm going to note here. One of them is just because we're trying to put more and more into these enclosures. We're getting 1.2 meter racks. We're trying to put a bunch of drives. We're trying to put as much as we can, which increases the flow impedance. You increase the flow impedance, you have to run your fans higher or get higher power fans to be able to pull air, enough air through the system. In some cases, we're putting more higher power CPUs in these systems. Again, you need to have more flow to be able to cool those CPUs down. And another reason is just data centers trying to increase their TCO. They may increase their data center ambient temperature. And as you increase your data center ambient temperature, again, you have to increase your fan speed to be able to account for that change in inlet temperature to your system, to keep all the components below a certain level, whatever that level is for your system. Now, fans or AMDs can cause noise, and there's various reasons. One is it could be because of mechanical components interacting or coupling with the chassis. Another reason is just the broadband fan noise. I've seen papers where they've taken blades off of a fan and they run tests and you still get this noise. The motor itself creates noise. But then you got airstream turbulence. You got all this other broadband noise that's created. Another one is, and I've talked about it a little bit already, is those spikes that we see, those tones. And that's caused by a rotating impeller, rotating fan blade next to something that's stationary. It could be a stator, it could be a finger guard, it could be a connector, right? There could be a number of things that are there, and depending on the geometry, how close it is to that blade, it can cause these tones. And if you know the number of fan blades, and you got this, you get an acoustic plot, you get this acoustic versus frequency, you can fairly accurately determine what the fan speed is, or vice versa. If you know the fan blade and you know what your speed is of your impeller, you can see these blade pass frequencies, and you can see harmonics of them. You see the first one, then you can see harmonics afterwards, and it's really interesting to see almost all those tones, almost all of them are blade pass frequencies. So one of the things that we looked into is what if we use blowers? What if there's something else that could be used instead of just the axial fans to try to reduce that noise? And we worked with Boyd. Boyd has what they call as well, first of all, the blowers, I've done some research, and several places have said you can get maybe 6 to 15 dB reduction in noise by using blowers than by using an axial fan. And the reason is that in blowers, you have a lot less tonality, and one of the reasons is because blowers, instead of having maybe 3 or 4 blades, they have 15 or 30. I'm not sure exactly how many, but each one's different. They have a lot more blades that are doing work on that air. So instead of just having 3 or 4 or 5 axial fan blades, you can have a bunch of those forward swept or backward swept blades in an impeller that's doing that work on the air. The other part is, so it's shared. The other part is that the wakes from these blowers hit a single relatively radius blower cutoff versus an axial fan, which is just right there next to whatever static components that are there. So we worked with Boyd. They had a double width, double inlet blower, a DWDI blower. It's essentially 2 blowers on the same shaft. You have 2 inlets, and then you have the 1 exit. And they did some testing. This is some testing that they did compared to an axial fan versus a blower at the same operating point. And you can see there's 2 big things. One is you can see that the blower is almost always about 5 to 10 dB lower, except at the way low frequencies. And then you can see a lot of those tones, a lot of those spikes on the axial fan. And you don't see as many of those, and they're not as prominent on the blower. So those were two things that kind of made us think, hey, maybe this is something that we should look into some more. And we wanted to do some testing in an actual enclosure. Now, one thing is, I'll show it. The DWDI blower that we used was just something that the Boyd had at the time. It wasn't necessarily optimized for our system, and you could get a better acoustic plot if it was more optimized for the system that we ended up running it in. So we took just a single high-density storage enclosure. We ran it with the axial fans. We measured the pressure drop across the system. And then we took the blowers, we took the fans out, put the blowers in, and we increased the blower speed until we got the same delta P across the enclosure. That way it's the same operating point, so we're comparing apples to apples. And this is what we found. We did the HDD runout testing, and we found a 20% improvement. It could be more than that if that DWDI blower was actually optimized for that system. For those of you that don't know, maybe all of you do, but runout, in general, it's a slight error in the rotating tool, such as being off-center or not exactly round. So each of these discs, maybe it wasn't centered exactly on the shaft correctly, or maybe it's just not totally round. And part of this runout, it's a combination of repeatable runout versus non-repeatable. Repeatable is something like, hey, the disc is maybe a little bit ovalized, or maybe the disc isn't centered. So every time it turns around, it does the same thing. It wobbles or does the same thing, and the drive can kind of account for that. It's a non-repeatable runout that usually causes more problems, and that's what's caused by these vibrations, whether it's caused by acoustic or operational. But we saw this 20%, approximately 20% improvement going to these blowers versus going with the axial fans. So in kind of an inclusion, it's been stated, I think all of us know, or most of us know, the HDDs can be affected by these vibrations. They're sensitive to it, and we need to, and it's becoming more of a problem with the AMDs coming at higher fan speeds. Higher power applications, servers, more dense, higher ambient temperatures is causing these AMD speeds to increase. And if we can reduce that acoustic or attenuate that acoustic to the drive's performance, it will improve. And what we found in this testing is these DWDI blowers produce significantly less noise than the axial fans do. Just really quick, I'm just one person. There's a lot of people that helped out with this, Boyd Corporation, and there's a number of people at Seagate that helped me put this together, or help with the testing, or help decide what kind of tests we needed to do. We got Evgeny and Kevin, Josh Schaefer, Ted Wiegand, Charlie Morris, and Kevin Van Pelt. All these people at Seagate, as well as the Boyd Corporation, were big help in getting this done. So kind of call to action is, first of all, just kind of reminding us all that as we build these enclosures, these storage enclosures, we need to think about the acoustics to the drives, and vibration in general, right? How well the drives are mounted into the system, how well we damp the drive-to-drive interaction, but also what ways we can cool these drives in an enclosure to keep the acoustics down. One of the things, it's been presented, I think, Matt Shumway was talking about it before, and I think if you go to the Expo Center on the experience side, they have the OCP surrogate, storage surrogate. There's an HDD surrogate, it has 2 microphones on it. You can use that, you can put it in your rear slots in an enclosure, and it can provide an estimate of how well it's going to do as we increase the number of tracks per inch in these drives. As it gets more and more dense, you can kind of get an idea of how well your system is doing acoustically. That's all it's really checking at that time. And then just kind of encouraging everyone to get involved in the vibration storage subgroup. So that's my presentation. Are there any, I don't know if we have time for, I think we have a few minutes for questions. Are there any questions? Looks like that's a no.